Swayam Prabha. Digital India. Educated India.
So students, today I will teach you again some new questions, some problems on nanobiosensors so that you can plan accordingly. The kind of questions may come during your exams. Also at the same time, these questions help you to think some more course related questions. So this is kind of improvement your independent thinking. So let's start one by one. So today that's why I will cover the mainly the tutorials, the kind of questions may come in the exams. Also you can think independently, the kind of questions may arises during the discussions of the nanobiosensors or during the when you think something new project, that time you also may think this kind of problems. So first of all, first question is describe a ECC redox cycling mechanism to obtain a lower limit of detections. Okay, so let's show you the this question's answer. Means if this kind of questions come, how to solve it. Also at the same time, you can think like if you want to get the lower limit of detections. Lower limit of detections, this is also kind of your sensitivity, right? Your sensitivity of your biosensor, right? So if you design some biosensors, how sensitive is biosensors? For that you have to think about your limit of detections, that is called LOD. So first you have to design a ECC based biosensor. So let's design like this way. So because the question is describe ECC redox cycling mechanism to obtain the lower limit of detections. So let's first design and then describe the mechanism and how to improve the lower limit of detections. Okay. So from the name itself, you can start thinking to design and to think about the mechanism. So ECC means electrochemical, chemical, right? So that's why ECC. So we are saying this one ECC redox cycling. Okay. So let's first draw a basic ECC redox cycling scheme. Okay. Then you can explain the mechanism. So I will draw it. First, like if you have a electrode surface, this is a transducer surface. This is transducer surface, right? ECC means here you have to think like electrochemical, right? Maybe your oxidations happen, and then so this is, so you should have a compound A and compound B in some generic way. You first think A, so it is oxidizing on the surface, so A should be oxidized or reduced form. So it is oxidizing, so it should be in the reduced form, right? So it is reduced form, right? So A should be in the reduced form, and B after oxidation, so B will be in the oxidized form, right? So now you want to convert B to A, so you need some again here like this. So again you need something so that B can be again, it should be like this, means the arrow you have to start thinking how you should put the arrow. See, so A already B already oxidized to the means it is oxidized form. So, you have to convert B to A. So, you need B to A conversions, you need a reducing species, right, so that B can be again reduced. Suppose you have a compound C, right. So, your C is the reduced form, right. C is the reduced form, that is why C will reduce B to A and itself will be oxidized. So, D it will be the oxidized form, right. Now, you have to convert this D to C again, right. So, this is the, so this step is the electrochemical step, right, electrochemical step, and this step means B to A formation. This is the chemical reaction, the B to A formation is the chemical reaction. So, this is the chemical step, chemical reaction step, right. Now, one more chemical reactions will come, that is D to C. So, you need here D to C means you need one reducing agent, right. So, let us put on reducing agent, any reducing agent. So, E to F. So, this E to F, so A is the again you know E is the reduced form, E reduced form, and F is the oxidized form, clear. And these reactions E to F, these reactions again the chemical reaction, clear. So, you have to explain the mechanism like this way first. So, let us summarize this mechanism. How? So, first you have to think that some chemical reaction, this is the very basic stuff. So, see, I just represented it like A, B, C, D, E, F like this way, means. So, it is a ECC redox cycling, ECC redox cycling, okay. In this redox cycling, so it is the oxidation base. In the electrochemical oxidations happen on the electrode surface. So, on the electrode or on the transducers, you are oxidizing a substance, that is A, right. So, this A should be reduced form, this is in the reduced form, and it form a B, that is oxidized form. So, you have to take a again reduced form, any C that should be in the reduced form, so that your B will be converted to A again, and naturally you know the redox reactions, reduction, another is oxidation. So, reductions to oxidations mean it will release the electron, oxidation to reductions mean it will accept the electron, right. So, when your C, your B will convert to the reduced form, so naturally your C will convert to the again the oxidized form, because it already released the electron to the B, that is why it already released the electron, itself oxidized, so it is oxidized form. Now, you have to convert again D to C, so then you have to use a reduced form of on another reagent, that is E. So, E is the reduced form, and then you convert it to this D to C again, and its E itself converted to F. So, I am not going more cycling. So, just one electrochemical, one chemical, and another is chemical, two chemical, one electrochemical. This is the one mechanism for the ECC redox cycling. Just try to remember, here I am always saying in the surface is the oxidation, right, oxidation happen on the surface, but why not you are thinking opposite way? Maybe we can think on the surface reductions can happen, right. Base means here actually we are applying some oxidation potential, suppose 0.3 volt, right. If you take like ruthenium 2, if A is the ruthenium 2, suppose for example ruthenium 2, then B is the ruthenium 3, and if C is the aminophenol and this one D is the quinonimine, and E is suppose for example T shape, and F for example this one T shape O. But we can think the opposite way, right? Let's use ruthenium, means somehow on your electrode surface a ruthenium 3 can be produced. So means your ruthenium CV something like this. So here we can see like generally ruthenium cases, this one 0 and this side is the negative and this side is the positive. So mainly we are getting the oxidation potential and reduction potential very close to the 0. It is minus around 0.05 volt. This is the E half value, right? E half value you can remember, like E half equals to E of the peak potential of the anodic peak potential plus E of the peak potential for the cathodic divided by 2, means this is close to 0. And if you apply like around here 0.3 volt, then naturally oxidations will happen on the electrode surface. Now let's think if you want to apply the negative side potential like minus 0.3 volt. So in this case the reductions will be predominant. So opposite way, like if you have on the surface ruthenium 3, right? So let's show you like opposite phenomena. This is oxidation based. Just I will show you very briefly the reductions based. Let's show you. Reduction based will be, so suppose ruthenium 3, so it will reduce, right? So it will get the electron. It will get the electron. So you have to apply some negative potential. Okay, suppose minus 0.3 volt you are applying. So ruthenium 3 will form ruthenium 2. So you have to oxidize now ruthenium 2 to ruthenium 3, right? So you can remember I taught you already that can be oxidized maybe in the presence of methylene blue. So ruthenium 2 is forming the ruthenium 3. So that ruthenium 2 can be converted to ruthenium 3 again if you can use methylene blue oxidized form. So ruthenium 2 can be oxidized to ruthenium 3 and itself methylene blue will form the reduced form. Clear? So it is the reduction based. This is reduction based, and first one I have shown you, that is oxidation based. Now again, like now in your surface you have the methylene blue oxidized form that already oxidized ruthenium 3. You have so methylene blue ox actually converted to methylene red. Now you can convert again methylene red to methylene blue ox by using some oxidizing form, some oxidized form of something you can try. That can convert the red to ox again. So like this way you can design some new scheme. As I told you at the very first class, to get the limit of reduction, ECC redox cycling case, see there is one cycling, another cycling, then there is a oxidations or reductions happen. Because of the cycling reactions on your surface, electrode surface, your like the starting that you are going to oxidize or reduce on the surface, that will be repeatedly, it will generate because of this cycling, and it will generate very high concentration because of many cycling. Very high concentration of these things and will generate the high current, and very high current means you will get the, you can amplify the signal. Your signal to background ratio you can easily amplify. You can get lower limit of detections. So how ECC redox cycling actually helping to get the lower limit of detections? Because this many cycle will generate on the electrode surface more this oxidized species or reduced species, whatever you want to oxidize or reduce on the electrode surface. Its concentration with time will increase and you will get high signal. Naturally your limit of detections will be so very low, very sensitive. you will get highly sensitive biosensor. So, next questions now. So, in this tutorial I will teach you again some very important step, that is the biofunctionalization that I already taught you. So, let us summarize the biofunctionalizations, how you can use this biofunctionalization process for biosensor development. Here I asked you questions. So, this question is describe a schematic diagram for the functionalizations of antibody. So, when we will ask this kind of questions, immediately just think antibody means, so it has many functional group, amine group free, that all this functional, many functional amine group or carboxylic group free, COOH. So, COOH or NH2 group you have, that you have to functionalize on the graphene oxide surface. So, graphene oxide, graphene oxide, it is the nanomaterial for carbon based nanomaterial. It is carbon based nanomaterials. So, this kind of nanomaterials will be very much useful to functionalize different biomolecule on the surface. See, you have the transducer surface. So, before the fabrications of graphene oxide, you have to clean the surface. That is very common, that you have to follow. So, first you have to clean the surface. The cleaning method I already taught you. Then you will have lots of hydroxyl group on the surface, because this surface will be very much hydrophilic. This surface is very much hydrophilic after the cleaning, hydrophilic. So, what is the hydrophilic? Hydrophilic, it can attract the water easily. So, if you measure the contact angle means hydrophilicity, hydrophobicity we are measuring now. So, if you measure the contact angle, so your water droplet will be like this, means you will get lower contact angle. But if your surface is not cleaned properly, then you will get, means in this case you will get the water droplet like this, means your contact angle will be very, very high. Now, you just drop cast your graphene oxide on this electrode surface. You have to follow the drop casting. Drop casting means some graphene oxide you can prepare in a test tube, and you have to disperse it in a water, DI water, in a solution you have to disperse it. Then you can drop cast, means just drop it on the sensor surface. Then you have to wait for drying. Once it is dry, then you can use for antibody immobilization. So, once your surface dried, so it will be covered by graphene oxide, and graphene oxide also has many functional groups. So, one important functional group is the carboxylic acid. Okay. So, it also has some carboxylic acid. So, now let us come the functionalization. So, your antibody contain amine group NH2 and your graphene oxide that contain carboxylic acid. So, now COOH and NH2 group, you can couple these two, they can form the amide bond, right. But this amide bond, they are thermodynamically they can okay, but kinetically very slow. So, that you have to use EDC and NHS. They can catalytically, they can react each other, and very fast they will form the amide bond on the surface, and your surface will be ready, like the nanomaterial coated, that is the graphene oxide, and your antibody will be immobilized on the surface. Now, this sensor surface is ready for the detections. Clear? So, like this way you can draw a schematic diagram for the functionality of the antibody on the graphene oxide surface. Okay. Okay. Now, next questions. This is the very important class I took last time, like sodium borohydride treatment on the nanoparticles and use them for biosensing applications, right. You just remember the NaBH4, right. So, if you want to treat some nanoparticles, suppose you want to treat your gold nanoparticles, right. So, your sensor surface, maybe you have some primary antibody coated your sensor surface, and if you drop your target like antigen, it will bind. Now your secondary antibody, that is conjugated with gold nanoparticles, right? That you can use this gold nanoparticle for the sodium borohydride treatment. So what happened the sodium borohydride treatment? So if you sodium borohydride means Na plus BH4 minus. So this borohydride, it will form atomic hydrogen. Atomic hydrogen. This atomic hydrogen will adsorb on the gold nanoparticle surface. This all they will adsorb, and because of this hydrogen adsorption, it will form a very this surface become highly active, right? You can remember highly active surface. So this mechanism you can mention. So once this secondary antibody, antibody 2, this is antibody 1, antibody 1, when this antibody will come, secondary antibody with gold nanoparticles, as it is highly active, that will be very useful for signal, very good signal amplification. So you get very high signal because it is very much active. Even last time I told you, instead of gold you can try palladium nanoparticles also, because the activations of palladium nanopart is very fast. Also you will get very high signal with sodium borohydride. So the reason is this, that hydrogen adsorptions can happen on the outer surface and it will activate the surface. It will form because of surface reconstructions. So there is a chance of to get the high signal, and naturally your limit of detection will be very low. Okay. So if your limit of detection is very low, then your biosensor will be called the ultra sensitive biosensor. Ultra sensitive biosensor. Okay. So like this way you can think how to design a ultra sensitive biosensor, how to get a lower limit of detection, very low limit of detection you may get, and where you want to apply this sodium borohydride treatment, how this treatment happens. This is the mechanism. Clear these questions? Okay. Now let's come another questions. I think that also I taught you. Now let's show you systematically how to answer these questions. First question is, what is the reason for cyclic voltammogram shift to the right and then left as shown in the attached figure? See, first from left to right, this cyclic voltammogram is shifted from, so this is the number 1, number 2, number 3. So this is the minus to plus. You can remember the left side is the negative, right side is the positive. This is called potential window. You can remember potential window. So we'll scan a negative to positive, positive to negative. So this whole scan window is the potential window, and based on the positions of this potential window, we can decide the activity of your electrode surface. If you add some reagent on the electrode surface, how it will behave, means it will react fast or it will react slow, that this cyclic voltammetry can give you the information. So cyclic voltammetry is really important tool, really important technique that can guide you that how your surface behave. Based on the cyclic voltammetry positions, based on the cyclic voltammetry current, you can think. See, so what is the reason for cyclic voltammetry shift? See, in the number 1, in this number 1 case, you are getting, so total 3 cyclic voltammogram. So here your oxidation potential, this one E1, number 2 case your oxidation potential E2, and number 3 case your oxidation potential E3. See, these oxidation potential actually slowly shifting from left to right. So you need more energy basically to oxidize this species on your electrode surface. So in this case you need less energy, and this surface is highly, that's why you can say electrocatalytically active. So, your surface is highly electrocatalytically active because you can oxidize the species. Suppose for example, this is the glucose oxidation, glucose oxidation. So, you are oxidizing glucose on this surface and it can be oxidized easily in the very low, means the negative potential, the low potentials. So, you can say this surface, so you can think like three surface. So, number one surface is electrochemically highly active. This surface is electrochemically highly active because it can be oxidized very easily. But in the second case, see, shifted. So, why this shifting can happen? It can be because of the aging, because of the contaminations, or because of the your biomolecular fabrication. Suppose you have the very bare gold surface, so you may get this kind of cyclic voltammogram. Now, your bare gold surface, you already immobilize the antibody. So, after immobilization antibody, definitely your surface electrocatalytic activity will decrease, and because they all are the protein, they are kind of non-conductive. That is why it means your substrate can be oxidized in the higher potential. You need higher energy to oxidize this substrate. That is why this cyclic voltammetry proves that your electrode surface is moderately electrochemically active. Moderately electrochemically active. Okay. Now, third step, third cyclic voltammetry, it is showing that again shifted towards right. So, it means if your sensor surface after the antibody, maybe you are adding here BSA, right, bovine serum albumin, so that you want to block the other empty part, so that you can minimize the non-specific binding. So, your surface now looks like this, antibody, and so that is nanomaterial somehow, and here BSA. So, BSA, and so that is why your surface become little bit again non-conductive. So, it may be lower electrocatalytically active. So, like this way you can characterize your surface step by step, that yes, your surface actually modifying by it is modifying by some and as you added the antibody, yes, antibody is there, you added the BSA, that is why it is decreasing. So, like this way you can characterize the surface. So, reason is that is why the main reason is that the electrocatalytic activity actually decreasing when you are moving from left to right. There is another phenomenon like aging effect, I told you, like aging phenomena. Last time I told you, no, that gold nanoparticle, if you have coated the gold nano on the surface, if you kept a long time like 1 month, it can decrease the surface. Then if you check the cyclic voltammeter, it can shift here. But now, if you add the sodium borohydride and if you can activate, then again you can see the shifting from again right to left. It means again electrocatalytic activity increasing. So, this is also because of electrocatalytic activity shifting from lower to higher electrocatalytically active your surface. That is why. So, this is the reason. Like this you can explain. See, so like this today I just discussed this all the questions that actually help you how to design a sensor and how to explain. Definitely, if you can explain, then only you can move to the next step. So, generally when we characterize some biosensor, when you design some biosensor, every time we are characterizing by using the cyclic voltammogram or by using impedance spectroscopy. The next tutorial I will teach you some impedance spectroscopy also kind of problem, so that you can use them for biosensor characterizations, and you can conclude yes, your sensor is already formed or not, right. So, this kind of problem actually basically help you to characterize. Okay. So, that is the conclusion for today's talk, that just think the problem and how to solve this, and this problem can guide you to go to the next level. Like if you have one problem, just think that another problem may come from this, and you may get lots of other solution, and you can design some new sensors. Okay, so that's all for today's tutorial. Thank you.